Good morning, Michael. I see we are back to our friend L'Hopital.
L'Hopital's rule, and we're doing a special case here. The case we explained earlier was when we had two functions and they were both going to zero. And you want to say, well, what happens to the ratio? Here we're doing something a little bit different. We have two functions, f and g. But now instead of these guys going to zero, we're saying they grow, and they grow to infinity. So this goes to infinity as x gets close to, well, I could say zero, maybe I'll say just some x0. It could be something like 10 or 3 or whatever. And the same thing for g. G of x goes to infinity as x gets close to zero. So instead of they getting 0 over 0, we get infinity over infinity. And we want to say, what happens to that ratio?
For some particular x naught.
For some particular x naught, that's right.
Okay, so the real issue here is when we did 0, that was a specific case, a specific number. It's a counting number. This is not a counting number. So what is it?
Well, you're right. It's not a counting number, but what this is expressing is this idea that f and g are growing without bounds. So eventually, they get bigger than any big number I want.
Oh, so let's start with a big number.
So what's a big number?
A million's a big number.
A million's a big number. So here's a big number, a million. And what this is saying is eventually, once x is close enough to x naught, we'll say f of x is bigger than a million when x is, let's say, really close. Oops, when x is really close to x0.
But that's a small big number.
Right.
So I want a bigger big number. Let's say 100 billion.
100 billion. Okay, so this is kind of like a little game. I'm saying closer and closer to infinity, which means bigger and bigger. So here is 100 billion. Can you write down 100 billion?
I'll write down 100 billion. I'll say 100 billion. So that's 100 with 9 zeros. I'm going to get tired. But that's not a very big number. We can have a number.
I think that's only 100 million. You
want 100 million. I'm out by 3 more zeros. See how hard it is to write 9 zeros, and I only wrote down 6. But that's a small number. How about a Google?
What's a Google?
Well, we'll start writing it down.
Oh, I don't think we have enough time to write it down, Matt.
Well, how many zeros have I got so far?
You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's a big number.
With 100 zeros. Now that's a big number.
So you can write it as 10 to the 100th power, which is a very, very big number. But again, I'm saying if f is going to infinity, I say if x is close enough to x naught, I can have it even bigger than this. So I could even have f of x bigger than this for x small enough, close enough, close. So really, really close to x0. So what I'm sort of thinking of is I'm thinking of an interval on the right-hand side is infinity, and the left-hand side is maybe something like, okay, I'll use a smaller number so I can write it in there. So I'm saying that f of x is eventually in this interval.
And we always, so now the analogy with 0 is interesting because in the 0 case of L'Hopital, we say close to 0.
Right.
And now we're saying this, which is really a representation of this process. A number as big as you want rather than a number as small as you want.
Right, a number as big as you want. And so now we're treating infinity like other numbers. So for instance, I can talk about numbers that are close to, for instance, 2. Everything from, let's say, 1.99 to 2. This is an interval that contains numbers close to 2. This we think of as an interval of numbers that are close to infinity. Everything in this interval is an actual number. It doesn't include infinity. Just like in this interval, it doesn't actually include 2, but includes a whole bunch of numbers that are very, very close to 2.
I guess the difference is in our brains. We associate these kind of numbers as a counting number, and this is kind of a process number.
Yeah, we sort of think of infinity somehow way, way out there that we never actually get to. Think of a little ant who's very, very slow walking along a branch, and at the end of the branch is length 2, and the ant maybe never gets there. It's kind of like us walking out to infinity. We never really get there.
Well,
There's
I
enough
don't
room
want
to
to
do
be
math.
like the ant. Thank you.
Thank you, Matt.